Hello everyone and welcome to another problem solving session on Special Maths Academy. And in today's video, we are going to cover the second problem from the just concluded Pan-African Mathematics Olympiad 2021. And the problem goes like this. So this is a construction of the question, and as you can see, both angles that are indicated in the question appear to be equal. So while we make K to vary along segment AB, see that for all points, when K is on segment AB, both angles here are equal. So we're going to go through the solution to this problem right now. Okay, so now we continue. So I've added some other lines here which we are going to use for our angle chasing. Right now, the question asks us to show that this angle, that is angle P prime KA, is equals to this other angle, the angle PBT. So first of all, let's do some bit of angle chasing. So we know that by circle theorem, this angle here is going to be equals to this angle here. So that is like angle P prime AK equals to angle ATB. And we also know that this angle here, which is one of the angles they are asking us to show are equal, by circle theorem, angle between tangent and chord is going to be equal to this angle here. So now, if these two angles are to be equal, like remember they asked us to show that this angle is also equal to this angle here. If two of them are to be equal, it will mean like these two lines are actually parallel. So if you can show that these two lines are parallel, we'll be done. But that's not how I approach the question. Rather, I noticed that in these two triangles we have now, P prime, AK, and ETA, if this angle is to be equal to this angle here, to imply that the two triangles are similar. Why? Because we already have two angles matching up. AA, like when two angles are equal, it implies that the third pair of angles have to be equal because sum of angles and triangle is constant, 180 degrees. So if we can turn the question around and trying to show that these two triangles are similar, that is P prime AK and ATB, if we can show that two triangles are similar, then to imply all the angle conditions, imply that all the angles match up, and to now mean that we show that this angle is equal to this angle, and because this angle, the angle between the tangent and chord is equal to this angle here, to imply that we will get the angle condition in our question. So we can turn this question around to showing that these two triangles are similar. That is the way we will approach this question. So we are required to prove that triangle PAK is similar to triangle BTA, like in this order, like the order I wrote it. So but for now, we're not sure these two angles are equal, but we know that if these two triangles are similar, it implies that all this angle is going to be equal to this angle. I'm done with that question. But the only angle now we're sure are equal are these angles I marked in red now. The only angles left in our question. So a good way of showing, there are a lot of ways of showing similarity. You can use AAA, ESA, and many of them, but it's going to be very difficult to use AAA here because that will require only angle chasing, and it's going to be quite difficult to do that. So our best bet would be to use SAS, so SAS similarity. So if you can show that we know like an angle is equal, a pair of angles is equal in both triangles, you can show that the two sides of the triangles that form those angles, if they match up, like if the ratios are equal, then the two triangles will be similar by SAS. So basically, if we can show this ratio is true, let's say PA over AK, can show that this ratio is true. That's because P prime A over AK. If we can show that it's equals to PT over TA, then we're going to be done. Why? Because it means that this over this is equals to this over this, and because the included angle, the angle between those two segments are equal, then the two triangles will be similar. We've done that question. So this is actually what we have done that question to proving that these two these ratios are equal. So right now it's going to be difficult to do it normally, but we're going to use a little bit of angle chasing before we apply trigonometry to do it. So first of all, we're going to introduce some angles now. We're going to introduce some angles. Let me clean out this thing. Red angles here. So we can let's call this angle here Let's call the angle here angle X. Let's call the angle here angle Y. This angle here is angle theta. So remember, K is a variable point on AB, so yeah, we can never like determine theta in terms of some other angles here. So like let's call this angle theta. So by angle chasing, like since quadrilateral TKPB is cyclic, you know that this will also be theta. You know that then because this angle between tangent and chord, you know that this is going to be X. And by the converse of that, you know that this is going to be Y. So now to find this angle here is just going to be, since we have found all the other angles in triangle ATB, this angle is going to be 180 minus their sum. So basically this angle is going to be what? 180 minus X plus Y plus theta. So now, the way I'm going to use trigonometry to approach this question is I'm going to find AK over KB in two different ways. Like I'll try to find AK over KB using triangle ATB. And later on, I'll do that same. I'll find the same ratio using triangle TAB. So we know that because the same ratio we're finding, those two values are going to be equal, but they are not going to be identical. Like we're not going to have something like maybe sin X over sin Y cos sin X over sin Y, but we're going to get some ratios involving these triangles X plus Y, X, Y, and theta that will be equal, but they won't be identical. And those are kind of things we like. So first of all, as I said, I'm going to find this ratio in these two triangles. So let's start with this first one now. So finding this ratio using triangle ATB, that is this obtuse angle triangle. Okay, so how are we going to do that now? Since we have chased all the angles in that triangle, we can then let's say where I usually approach questions like this. So what I'm actually going to do is I'm going to find AK over TK. And later on, I'll find KB over the same TK. And after this, I divide these two ratios. So AK over TK, we can find that using sine rule. So AK over TK using sine rule going to be equal to sine 180 minus X plus Y plus theta all over sine Y. So this angle here and the numerator can be single. We know that by properties of sine, it's going to be the same as this. So this AK over TK. We are going to find KB over TK also using sine rule. So the reason I chose TK is because TK is a Servian in both triangles ATK and TKB. So that is the idea when we're using trigonometry like this. We try to use a common Servian to more than one triangle. Sorry, a common, and it's not, it's a Servian in the bigger triangle, but it's actually a side in those two triangles, not a Servian, sorry. So using sine rule here, we get that KB is facing angle theta and TK is facing angle X. So we have these two ratios now. So when we divide the first one by the second one, we are going to get that we can call this equation 1, we can call this equation 2. So when we divide equation 1 by 2, we're going to get AK over KB equals to what? Sine X plus Y plus theta sine X over sine theta sine what? Sine Y. These are first important ratio here. AK over KB is equal to this. So I found AK over KB in triangle ATB. This is what I meant by finding AK over KB in triangle ATB. Not all this. So we'll just write it here and note it down here. So AK over KB equals to sine X plus Y plus theta sine X over sine theta sine Y. Okay. So remember, let me just write it. Our major goal here is to show that these two triangles are similar. We have to prove P prime AK similar to P prime AK is similar to BTA triangles. Okay. These are first important ratio. We have found this in this triangle. So what we're going to do, we're going to use the same idea to find this same ratio in the other triangle we're talking about. That is like the triangle PAB. We're going to use the same idea. Okay, triangle PAB. So first of all, as I said, so it means we're going to find first of all, we're going to find AK over PK. Later on, we find AK. And later on, we find BK over PK. So we chose PK because PK is going to be a side of the two smaller triangles in this this bigger triangle PAB. That is triangle PAK and triangle PKB. So we want to find these two ratios. We divide it and find our AK over KB. So this is going to be equals to what? AK over PK, this bigger triangle PAB. So okay, actually I have not yet found what this angle will be in terms of x, y, and theta. So, but I found every other angle. So this x plus y, this x plus y, this theta. This last one is going to be 180 minus there. So 180 minus 2x plus 2y plus theta. So it looks quite similar to this first one, but it's not exactly the same. So now we go around in triangle PAK. AK over PK is going to be equal to what? Sine 2x plus 2y plus theta all over PK is going to be what? PK is facing the angle x plus y. That will be it. And in the other triangle PKB in the bigger triangle PA, the other triangle PKB in the bigger triangle PAB, we're going to get that BK over PK is going to be equal to what? Sine theta over sine x plus y. So I want to divide these two things. Okay, let's call this one, same thing. So the same idea we used to do this. So this is a common technique I use when I solve trigonometric problems. Try and find a ratio in more than one triangle, and I'll try and make sure I found all the angles here. And so that's why I brought in these angles to be able to find the connection between angles x, y, and theta. So when we do this, we divide 1 by 2. So what is it going to give us? And these two denominators are actually equal, so they cancel out. Same with the two denominators on the right hand, on the left hand side. So we're going to get sine 2x plus 2y. So this one is a bit special because actually the triangle is an isosceles triangle. That's why these two denominators are matched up. So this AK over BK is equal to this. So we can form a longer chain since it's the same ratio here. This also equals to what? Sine 2x plus 2y plus theta all over what? Sine what? Theta. So now it means that these two ratios here, second and third part of the longer equation, they are equal. So we notice that sine theta is common to both of them. And yeah, we can clearly cancel out sine theta. Why? Because K is the point on line AB, which is different from A and B. So like the angle theta cannot be 0. So that's why I can cancel. Clearly it can also be 180. Not to be parallel to the side and all that. So we can cancel it out. It can't be 0. More often than not in trigonometry, and when you see like two ratios are equal, generally you can cancel them out. But here we'll just verify that this sine theta cannot be equal to 0. So there's no problems here. So now, after all this trigonometry we have done, we now see that this remaining parts of this, so we're just looking at these two parts. It means that what we have left are equal. So that will mean that sine x plus y plus theta sine x is equals to sine 2x plus 2y plus theta sine y. We'll have that this ratio is equal. Don't know how we can use it for now, but to just have this equal, and it's clearly not obvious that it was equal from the very beginning. But we're just going to leave that, and we're suspecting that hopefully this equality we have here is going to be identical to us, showing that these two triangles are similar. If that can be the case, then it will be really, really interesting. So next up, now let's go back to this. I'm trying to show that these two triangles are similar. Okay, so that's like our claim. But remember, that's what the question is, and we are like 100% sure our claim has to be true. Why? Because if our claim is not true, our question is not going to be correct. So I know that our question has to be correct. So it means this claim has to be true. So we are sure it's 100% true. It's not just a random guess. So triangle P prime AK is similar to triangle PTA. So as I said, we know that this was the angle that we are sure matched up. So these two angles matched up here. So it's our best bet is like try to find the ratios that form these two angles, find the sides that form these two angles, and that's the ratio we prove are equal. So we won't like try to show that this over this is equals to probably this over this. So actually, it's better for us to show that this over this is equals to this over this, because we know that that angle in between these two lines are equal. But for the other two angles in the question, we're not sure if they are equal. We have not yet gotten that they are equal. So what that give us? That will give us like to showing this condition. That is going to be if and only if P prime A over AK is equals to what? BT over what? 80. Right? Okay. So actually, when we're done with this question, I see that it was not so necessary to use trigonometry, but for now, we just do as if we're not aware of that. So now, if you notice, most of all these ratios here, that is PT, AT, AK, there are things like we have worked before with in the past. So the only ratio here that is a bit tricky is this one, P prime A. We have not yet really gotten any ratio that involves something connecting to P prime. So, but now I'll use an interesting property in this question. Look at the definition of P prime. P prime is the reflection of P in point A. So by that definition alone, it implies that P prime A is going to be equals to PA. They're actually going to be equal. So we can actually replace this P prime A with PA because they are equal in magnitude. Yeah, but it doesn't necessarily mean that the triangle will change. Doesn't mean that we are going to like change our triangle to PAK or something like that. But because the two ratios, the two lengths are equal in magnitude, you can actually change it to this. So this one looks much more better to work with because P prime is kind of isolated and we have not done a lot of angle chasings involving point P prime. So it makes more sense to work with side length PA rather than side length PA prime. But because two of them are equal, they have the same length in trig. So yeah, that's another advantage of trigonometry. Once two things are equal, you can just do a direct replacement. So now P prime over AK is equals to this. Sorry, so PA over AK is equals to PT over AT. So this is what I want to show is want to show that this ratio is equal. How can we go about it? PT over AT. Okay, so now you see that triangle side lengths PT and AT, they are part of a bigger triangle PAT or BAT. And these side lengths and PA and AK are part of a bigger triangle PAK. So you can actually just use sine rule to find PA over AK, and then use sine rule to find PT over AT. And hopefully, if those two things are equal, to imply that these two ratios are equal and to imply a triangle is similar, we don't have that question. Now let's use in triangle. I say later on, you see that it was not so necessary to use trigonometry. So it implies that PA over AK is equals to what? So in this our triangle PAK, like PAK, angle line segment PA faces this angle here. Let's put this angle here. Let's try and find it in terms of all our angles we have gotten so far. This angle here. So this whole line segment PA face. So we know that this angle here in red is going to be equal to what? The sum of these two other angles here. This angle is the going to be sum of this angle plus this angle. So that is going to be what? X plus y plus theta. I see that somewhere we'll have sine x plus y plus theta here. So we're actually suspecting that what we have here will somehow match up to what we have here. But let's just keep our fingers crossed. This angle is x plus y plus theta. Yeah, and AK, it faces this. Okay. So it means that PK over AK is equals to what? So PA over AK is equals to sine x plus y plus theta over what? Sine 180 minus 2x. This well, by property of sine, we can just write sine 2x plus 2y plus theta. This is what we have. Then next, in triangle BAT, BT over AT equals to what? So BT, so the triangle BAT is this obtuse angle triangle here. So BT over AT, I don't know the angle chasing involved in here already. So BT is facing sine y, and AT is facing sine x. So we'll have this and this for this. We'll see that all these four angles here are the same four angles that are included here. So we can actually try to rearrange these two in a way that we can try to get that these two ratios are equal. Let's just rearrange this first of all. So this thing I boxed in red here is actually equivalent to sine x plus y plus theta over sine 2x plus 2y plus theta being equals to sine y over sine x. So you can see that this ratio is true. Like this is a fact. We've gotten this is a fact. It's not something we guessed. It's a fact. But this one is, we're trying to now show that these two things are equal. But from this fact we got here, this left-hand side is what we have here. This right-hand side is what we have here. So by the fact above, it means that these two things are equal. So it implies that PA over AK equals BT over AT. So, but remember, PA was the same length as PA prime, so we can change this to this. So PA prime over AK equals to BT over AT. And also because we have the angle P prime AK is equals to angle. I'll show the angles now. The angles I'm showing in red now. Because we already have that these two angles are equal. Angle B CA. Then, using these two facts, it implies that by SAS, two triangles are similar. Triangle B prime AK and triangle BTA are similar. That's just actually what we wanted to prove. And remember how we say, like, if we are proving this, we are done with our question. So, because these two angles are similar, now what is it going to imply? It's going to imply that this angle here is equals to this angle here, not this angle, is equals to this angle here. This angle is actually going to be cos x in the long run. And also, it's going to imply that this angle here, I'm changing the color, going to imply that this angle here is going to be close to the last pair of angles, this angle here. So this angle is going to be y. And since this is y, and remember, by the converse of the tangent chord theorem, circle theorem, we get that this angle here is also going to be y, which I've already done earlier on. So this angle, so it shows like these two angles are y, and that's actually what they are supposed to prove. So I don't want that question. Because remember, we broke down this question showing that these two triangles are similar. Now, once we are done with that, we are already done with the question. So this is how to carry on in the question. But as I said, it was not so necessary with trigonometry because we could just play around with the question. We could just actually work only with the ratios without trying to find the angles they face. It was also possible to do that without like trying to do angle chasing. It's possible to also do that. So I'll just leave that to the viewers to try and figure out how you can solve this question without involving angle chasing, just using really similar triangles. Okay, the only angle chasing should involve these two angles here these two obtuse angles here that we should are equal. So like after we are done with our SAS, we now use the fact that these two angles are equal to complete that both triangles equal. But we do all these things without getting so many sign ratios here. So I'll leave that to the viewers to try and do. And this is all we have for this question. It was a bit interesting. Now we see that trying to like find the ratio, as for in this case AK over KB, more than one triangle is a common technique that used a lot in trigonometry to find different non-identical functions to be unequal. For example, these two things, they don't look identical at all, but somehow they're equal. Something we could have never guessed by using angle chasing. Something we could have almost never gotten by using only angle chasing. So this is the power of trigonometry, and it helped us greatly in this question. So this is all we have for today, and I'll see you some other time. Thanks for joining.